So we are not about to embark on a purely scientific excursions, but rather we shall explore the origins of Dmitry and mine artistic quest. Much of the short presentation will be devoted to the following topics: the electrolysis of water, the electron, and bubbles and droplets. For an artist to write the next chapter in the book of hydrosophy or adoration of water, and hydrosophy has a very, very, very long tradition. Water was revered since the longest time. So, however, it is no longer enough to marvel at the tempestuous sea, whispering streams, or the polished mirror of a lake. Behind its deceiving transparency, water holds deeply hidden mysteries, ensuring that our thirst to solve them will not be quenched so easily. And I would like to quote a saying by a Russian avant-garde artist from the beginning of the 20th century, Pavel Filonov. He did the paintings, very, very detailed paintings, and he was friends with some crystallographers. So if you look at his painting, you kind of see, I mean, this is like cubism cubed. You see an object that is falling into its crystalline lattice. So what Pavel Filonov, and he died of starvation in 1994. In
1914.
In 1940, at the siege of St. Petersburg. But his art was not accepted by the Soviet regime, and he couldn't earn money as an artist, and he died of starvation. However, today, and what he was saying was, our goal as an artist is not to imitate nature, but to imitate the processes of nature. And this is, of course, Paul's talk showed it very well how it could be done. So from the beginning of my collaboration with Dmitry, one of the conditions for us was never to create a solid state artwork. So our very first installation, Awakening Shrouds, was comprised of water vapor clouds produced by electrolysis. Our most obstacle-laden and celebrated work, Camera Lucida, that reveals an exotic phenomenon called sonoluminescence, during which sound triggers light emissions in water. And one of our latest artworks, Hydrogeny, exhibited upstairs, revisits artificial clouds. But this time it's clouds of hydrogen bubbles in water.
Just give you a moment to read this dramatic statement by one of our favorite 19th century scientists, William Crookes. One of water's many anomalous features is its capacity to behave as an acid as well as a base, a trait that it passed on to amino acids, making possible much of the chemistry that goes on in our bodies and in all living matter. So despite the fact that water is a poor conductor of electricity, its chemical properties are easily transformed in the presence of electric current. This was first recognized by the physical chemist Svante Arrhenius and later elaborated in biochemistry by Alexander Oparin, who was nicknamed the Charles Darwin of the 20th century. Known as amphoterism, this property happens to be based on polar molecular dynamics. Each water molecule carries a dipole or a net charge. This dipole causes each molecule to behave like a little magnet with a positive end and a negative end. The dipole also causes water molecules to be attracted to each other. The positive hydrogen is attracted to the negative oxygen of a nearby molecule. And as a result, the molecules are actually in constant motion, and the hydrogen bonds are continuously being broken and reformed. In fact, the average hydrogen bond lasts only a trillionth of a second. Nevertheless, in spite of how comparatively tiny hydrogen is to its neighbor, because there are so many hydrogen bonds, they exert significant force on the oxygen atoms with which they are so briefly interlocked. When the Earth's aqueous envelope is irradiated by sunlight, water is split apart into oxygen and hydrogen gas. Among the planet's quintessential processes, solar water splitting is the source of most of the oxygen in the atmosphere and the origin of all earthly hydrogen. This hydrogen also happens to helically conjoin every pair of DNA. In photosynthesis, water splitting donates electrons to fuel photosystem 2. Photosystem 2, or water plastoquinone oxidoreductase, is responsible for the electron transfer during photosynthesis, and it is the only protein that can procure oxygen from water and light. In the chemical industry, water splitting, also known as electrolysis, is a method of separating chemically bonded elements and compounds by passing an electric current through them. One important use of electrolysis of water and artificial photosynthesis, or photoelectrolysis, is to obtain hydrogen.
So here you can see an image of a close-up of an artificial leaf. So at the beginning of Raoul's talk, you saw an image of this artificial leaf, but here you can see what happens if you zoom into it. And it's another researcher who is engaged into the artificial photosynthesis and trying to bring us closer to the utopian economy of hydrogen fuel. Daniel Nocera from MIT.
Yeah, according to Daniel Nocera, in an article in Science magazine in 2008, by means of artificial photosynthesis, solar power will become unlimited and soon. One of the latest other, I would say, giant steps in terms of hydrogen power is the HECA project, the largest ever hydrogen plant, which is currently being constructed in California. But because Raoul, I think, covered extremely well the subject of energetics, using water as fuel, I think that we will make a leap back in time to some of the earliest electrolysis research, that of Michael Faraday, the grand old virtuoso of 19th century natural philosophy, as physics was called at the time. Since its discovery in the year 1800, electrolysis provided an ideal environment for examining the ambiguous phenomenon of electricity, as well as an ideal tool for precisely separating chemical species. In 1834, Faraday published his laws of electrolysis, stating that the quantity of elements separated by passing an electric current through a solution is proportional to the quantity of electric charge passed through the circuit, and that the mass of the resulting separated elements is directly proportional to the atomic masses of the elements being disassociated. This was the first experimental evidence that there is a natural elementary particle of electric charge which was not infinitely divisible. If we assume the existence of atoms of chemical elements, this is Faraday writing, we cannot escape from drawing the further inference that electricity also, positive as well as negative, is divided into definite elementary charges that behave like atoms of electricity. During electrolysis, each liberated hydrogen or oxygen ion, a term also coined by Faraday, ion that is, repels the liquid around it to form a gas bubble that is proportional in size to the discrete quantity of charge used to nucleate the bubble. Faraday's conclusions were perhaps the first evocation of electricity's quantized nature, and hence began the hunt for what was to be named the electron in 1894 by Irish physicist George Stoney.
He was actually from Trinity College.
3 years, this was in fact, 3 years later, J.J. Thomson identified the electron. And in fact, to him it was unthinkable that there was a particle smaller than an atom, in fact, 1,000 times smaller than a hydrogen atom. The electron was discovered within an ionized gas that was subjected to electric and magnetic fields, a Crookes tube of sorts. However, in the exact sciences, there is a tremendous difference between identification and detection. The latter being married to precise measurements. And so it was in the face of prominent German theorists still clinging to the idea of electricity as an ethereal wave, it took over a decade after Thomson's discovery to finally measure the quantum of charge. Having improved upon an electrically levitated water vapor experiment conducted by one of Thomson's assistants in a cloud chamber, Robert Millikan, using oil vapor instead of water, executed the first ever accurate measurement of a single electron in 1908. Meanwhile, the biggest revolution in scientific history was stirring. Max Planck, who had begun his career by proposing a thermodynamic interpretation of electrolysis, established that electromagnetic energy could only be emitted in quantized form, marking the birth of quantum physics. Nonetheless, the strife that was triggered by Faraday's investigations of electrolysis perhaps reached its ultimate peak just recently, in 2006. To observe the motion of an electron, an elementary particle with a mass that is a billionth of a billionth of a billionth of a gram, has been considered to be impossible. So when two Brown University physicists, Meurice and Guo, showed movies of electrons moving through liquid helium, the scientific community was astonished. A free electron repels the atoms that surround it, creating a small space or a bubble around itself. In conventional fluids, the bubble shrinks into oblivion because the surface tension of the liquid works against this repulsive force. Superfluid helium has very little surface tension, so the bubble can become much larger. The two opposing forces balance when the diameter of the bubble is about 40 angstroms, still far too tiny to see. The researchers used a transducer, and a sound-emitting loudspeaker, to saturate the volume of liquid helium with specific acoustic waves that when they encounter the electron bubble, they cause it to to alternately increase in size and decrease in size. And during the increase, the bubble actually becomes big enough to see with the naked eye. As you will see in just a moment. A strobe light is used in order to, that is synchronized in phase with the sound pulse. And that allows you to see the electrons kind of semi-frozen as they're moving. Most of these electrons travel in a fairly straight line leading away from the transducer, which produces, once again, an acoustic flow of heat through the liquid. A few of the electrons, however, follow a distinctly different snake-like path. The vortex, as Meurice and Guo write, is like a piece of string running through the liquid. The electron bubble is attracted to the core of the vortex and gets attached to it. It's as though it's sliding down this rope that winds through the fluid. These winding electron bubbles seem to evoke the hydrogen bubble strings in our installation upstairs, hydrogeny. Indeed, for me and Evelina, among its most striking aspects is the expanded visibility of a bubble's spatiotemporal evolution. These micro lenses assemble into such a fine mesh which volumetrically maps the slightest perturbation of the water. And these perturbations, which cause the swirling motions, which you will notice, are actually occurring in accordance with the nucleation of the bubbles at the electrodes themselves. And during the first phase of growth, a bubble nucleus inflates linearly with time. At the second stage, bubble growth is limited by the diffusion of gas within the liquid, causing its size to increase as the square root of time. The final phase before detachment is limited by the kinetics of dissolved gas production, causing the bubble to grow as the cube root of time. One of the precursors to hydrogeny, to this work, also involving water, whirling bubbles, and light, is an installation called Camera Lucida, which we had the fortune of exhibiting here at Science Gallery during the first light wave edition. Sonicated, just like the electron bubbles in the liquid helium experiment, which allows you to observe individual electrons, here microscopic gas bubbles collapse in an acoustic field, at which point they reach temperatures as high as are found on the sun. And it's at that moment that light is emitted. And it's for actually much less than a billionth of a second. But because that light repeats per sound cycle, we are able to see the shape of those sound waves, and we kind of interpret this light in a semi-continuous fashion. And it can only be observed in total darkness.
And this is also another aspect of how acoustic waves can influence water in a completely different fashion than what Paul told us about. And it is interesting indeed that the scientists in the electron experiment from 2006 used the same techniques in inflating the bubbles with sound waves as we used in Camera Lucida.
We're going to watch a brief fragment of this piece, so if we could turn the lights down slightly.
And the original precursor to our hydrogeny piece, another work that uses electrolysis, was a work, our very first work together, called Awakening Shrouds, where we used superfine water vapor, so very, very fine mist, used by electrolysis, in order to project images. So what we would create a cloud the size of a human body or a little bit less, kind of friendly size cloud, and only in a particular angle of light accidents you will see the image on this cloud. And if you have a couple of projections as you walk around this cloud, you will see different images from different angles. And actually the inspiration for the naming of this piece also came a little bit from Ireland, because we are great admirers of Finnegan's Wake. And our first work starts with the same word where James Joyce ended.
Yeah, and also I think that this piece is evocative of the charged vapor cloud experiments conducted by Robert Millikan that we mentioned earlier, and also by J.J. Thomson's Cavendish lab that discovered the electron, where they were using water vapor also emanating from an electrolysis cell. So if we could dim the lights again, thanks.
Thank you very much, and you can watch a little fragment of Awakening Shrouds.